Yeah, so we can start now.
Excellent. Welcome back. This is, let's move on to the second part of the tutorial and the first topic. So I think for the second part, we'll have a succession of different modules that are shorter in time. The first topic is data fragmentation. And this is the divide and conquer approach to compressed sensing. And what we have is the following. So we already argued at the beginning of the talk that if we cannot do a compressed sensing problem that is huge, say where the matrix width is 2 to the 128, then maybe we can break it down into small components. But there were some challenges with doing small components. So what do I mean? You can break 128 bits into fragments of 16 bits. And there, for 16 bits, the width of the matrix is 2 to the 16. So it's then amenable to traditional compressed sensing techniques. And then we said, okay, so we can do compressed sensing on the level of a small packet. But there were some unresolved issues in the sense that if you do data fragmentation and you do some sort of compressed sensing on the small fragments, then you get lists of fragments as the output of your decoding. And then you still have to somehow, you have to devise a way to be able to stitch the fragments together or pick a fragment that was in the first slot and say, I'm going to pair it with a fragment in the second slot and the third slot and so on, so that you can recover a message. And we know how to do that well. So what we can do is before fragmentation, what we're going to do is we're going to use an outer code. So the outer code is going to add some redundancy in a structured fashion to the packet. So maybe say, for instance, I have a packet of 128 bits. If I decide to use a half rate code, then I'm going to have 256 bits that I can fragment. I can send each of them in a small compressed sensing fashion, and then I can use my outer code to stitch the different packets together. And this is the idea that led to coded compressed sensing. So let's look at that. So again, we're in a situation where we have, before fragmentation, we have a very large sensing matrix. The number of rows is the number of symbols that we're able to transmit within a frame. So it's in the order of 30,000. And then the number of columns, because it's a signal dictionary, is 2 to the number of bits in my message. So if I have 128 bits, then it would be 2 raised to the 128, which is by any standard CS solver huge. And so what we can do if we do data fragmentation is we are going to say, I'm going to fragment my original message into L fragments. And then I'm going to index these fragments separately. And then I'm going to stack them into a vector. So what do I mean by that? In this small example, I fragmented my message into 2 bits fragment, and then I index them. So if I index 2 bits, I get 2 to the 2, which is 4. So I get a little section of 4, and I have an index vector. So there's 1, 1, and zeros everywhere else. And then the same thing is going to be true for the second fragment, the third fragment, and so on. And so what happens is if you decide to do fragmentation into L fragments, you're starting with a total of B bits, capital B bits. You're dividing by the number of fragments, which is L. So you're going to get L little indexes, each of length 2 to the B divided by L. And the reduction in width of the matrix is quite drastic. This construction is also similar, it gives you a vector that's similar to a sparse regression code, which is another type of object that's well studied in information theory. And so if you have a message of length 2 to the 128, and you fragment it into 8 fragments, then each of your fragments are going to have 16 bits. So one index vector is now going to have length 2 to the 16, and you're going to have 8 of them. So you have 8 times 2 to the 16 is the length of your aggregate index vector that contains 8 sections, each of length 16. And if you think about this, that's now 2 to the 19. So if you compare the width, original width of 2 to the 128, after you've done data fragmentation, the resulting width is now 2 to the 19th. It's much, much lower. And so the data fragmentation, if you remember, we saw this graph at the very beginning of the talk. On the x-axis, I have the undersampling fraction. And on the x-axis, I have the measure of sparsity. And we were stuck in that 0, 0 corner originally with the messages that we had. And now what I've done is I plotted the same points in terms of undersampling on the x-axis and sparsity, but I've done it from a fragmentation of L sections. I take my 128 bits and I divide them into L sections. So now you can track the undersampling fraction and the measurement of sparsity, and you get this point. The first point here is for L is equal to 8. The second point is for L is equal to 9, 10, 11. And you can see that it drastically changes the operational point onto this notional diagram that contains undersampling and sparsity. So now we have some breathing room, and we're able to reduce the width of the matrix into something that we can manage, or at least that's the idea. But we need to be able to stitch the different messages. So now I started with one immense compressed sensing problem, and I've been able through data fragmentation and indexing to reduce it into L compressed sensing subproblems. But if I do L compressed sensing subproblems, now I have a subproblem in slot 1, in slot 2, another compressed sensing problem in slot 3, and so on. Then when I run my compressed sensing solver, per slot, I'm going to get K fragments, but this does not tell me which fragment in slot 1 goes with which fragment in slot 2, as I mentioned earlier. So we need some sort of outer code to be able to stitch things together. So before I do data fragmentation, what I'm going to do is I'm going to devise things with an outer code. And the first article that we wrote about this is this 2020 a coded compressed sensing scheme for unsourced random access. And what it does is it adds redundancy in an incremental fashion where you add no redundancy to the first segment, and then you start to add a little bit more redundancy to the second, the third, and so on. And as you go down the slot count, you add more and more redundancy. So now you get L instances of a compressed sensing problem. And because they are of reasonable size, you can use something like a non-negative least square solver to solve each of them. You recover lists of K fragments per slot, and you use the outer code to stitch them together. The outer code works in the following fashion. So what I do is I'm going to pick out of the first list a root node. So in this case, I picked the second fragment as my root node. And then I'm going to go down the tree. I'm going to go to list 2 and look at all the fragments and retain only the fragments that are parity consistent with the root node. So here in this cartoon figure, I've used this green bits to represent some sort of parity, and that parity acts only on the section that's before it. So it acts on the information bits that are on this one, and if it matches the parity of the root node, then I keep it, and if it doesn't, then I discard it. So I'm pruning as I move forward in the tree. And so for every root, we build a tree of consistent fragments, and hopefully by the end, you end up with only one message, and then you've recovered that particular message. Okay, so what I want to say about this is in our previous SPCOM tutorial, we went to great length and explained how to build the outer code and how to choose the allocation of parity. And there's a natural trade-off between parity allocation and complexity. But because maybe some attendees were there when we gave our first tutorial, I've decided to talk extensively about something quite different this time. And so, so if you are very interested in this work, then I would say, I believe the SPCOM video tutorial about this particular tree construction are still available. And so I encourage you to look at them. What I want to do is turn our attention to a different construction that leverage some of the sparse graph technique that we've seen before. And before I do that, I want to take a few minutes and talk about compressed sensing in a different way. So I've talked about compressed sensing a few times already. And so the way I want to talk about it is the relation between compressed sensing and iterative solvers, and that will lead us into approximate message passing, AMP, as a very powerful algorithmic notion, as well as a proof technique. So what I have in mind for now, I deviate, I take a detour from unsourced random access. I'm going to consider a standard compressed sensing problem where I have my sensing matrix. This is this colorful matrix. And for now, I will just assume that it's a random Gaussian matrix. I have a vector whose sparsity is known, or sparsity factored as k non-zero entries. And it's the standard problem where I recover an observation that's of the form matrix times vector is equal to my observation, or I can think of it as folding this vector over the matrix. So everything is standard compressed sensing for now. And the optimization objective for my compressed sensing problem is I want to recover the vector. And what you will realize, because the length of the vector is very long, or the width of the matrix is large, then this is an underdetermined system of linear equations. So then a classical way to do this would be to find the pseudo inverse of this underdetermined system of linear equations. But I have additional information in the form of a sparsity in the vector. So I can, instead of just looking for the minimum L2 norm solution, I want to integrate the fact that my vector is sparse. And to do that, I'm going to take an optimization objective that's loosely of this form. I want to look for the argmin of this bioobjective function where there's the residual, that's my observation minus the matrix times that vector. So I'm looking at the 2 norm of the residual plus some weighted factor of the 1 norm of my solution vector S. And if you are familiar with compressed sensing, you will know that really what I would want to do is look at the 0 norm of S, but instead I'm going to look at relax this and look at the convex program and use the 1 norm. And we know that the 1 norm is sparsifying. So it's also a very good proxy for the compressed sensing problem. So now for these problems, there's extensive analysis with wide application. And what I want to say is, there are many ways to solve this problem, including a linear program, quadratic program, iterative self-thresholding algorithm, which we'll look at in some sense with and without momentum. There's some recent result that was quite a very nice work, and nonlinear least squares. And for these problems, we're thinking of a size of compressed sensing problem where we can use these, what has become these API'd out algorithms or off-the-shelf algorithms. Now, we want to pay special attention to iterative self-thresholding as a lead into approximate message passing. And we're reviewing approximate message passing because we're going to design an AMP algorithm eventually for our problem of unsourced random access. So here on this graph, what I've put is I've put kind of the basic optimization task for an underdetermined linear system. So if you have more degrees of freedom, then you have constraint, then you have an infinite number of solution. And if you think of an underdetermined system, what naturally you would want if you have no other information would be something like minimizing the 2 norm of S subject to the constraint that my matrix times S should be equal to my observation Y. And again, you have quite a large number, an infinite number of solutions because you have an underdetermined linear system. And I have also plotted the 4 fundamental subspace of a linear transformation. Here I have my linear transformation, which is my matrix phi. And if I take a tau vector on the right and multiply it by 5, I do synthesis and I go into my observation space that's on the left. And if I take a vector that lives in my observation space and multiply it by the transpose of phi, or if it were complex, the Hermitian or the adjoint, then it brings me back into the right, and the space is divided into these 4 fundamental subspaces. The reason why I want to look at is to introduce this composite iterative solution that lies at the top right. And I'm trying to do that because I want to give you a sense of where iterative self-thresholding and approximate message passing for compressed sensing comes from, if you're not super familiar with these transformations. So what we're going to do is we're going to use an iterative scheme. So we want it to be iterative because typically it's going to have low complexity. And so Z here, wait a second, I have to translate for my Indian/Canadian audience. ZT is going to be equal to my observation vector Y minus phi times my current state estimate ST. And my state estimate is going to be updated. I'm going to have ST plus 1 is going to be equal to phi transpose times ZT plus my previous estimate. So you're going back and forth between synthesis and analysis. And then if your matrix is such that the spectral radius of your matrix is less than or equal to 1, and you keep iterating this way, then this is an iterative way to get to the pseudo-inverse. So the pseudo-inverse is going to be your minimum L2 norm S subject to your constraint, linear constraint, phi of S is equal to Y. And you apply this composite iteration, it leads you to the right solution, which is over here. So I'll give you a minute to reflect on that. So my hope is that you are somewhat familiar with the 4 fundamental subspace, and then that you are also familiar with the pseudo-inverse. And maybe you know that the pseudo-inverse is the solution to the optimization task. Now, you may not have been familiar with this composite iterative structure to get at this solution, but you have to take it on faith that if you keep iterating here, then what you really get is the Newman series expansion, and then you get into the pseudo-inverse. Okay, hopefully you know this or you believe me when I say this. Because now what I want to do is use these equations, but in the context of iterative self-thresholding and approximate message passing. So what happens when you do when you have the compressed sensing problem is that now you're aware of sparsity. So you know that your state vector S is sparse in some sense. And so you know something on the right side of these fundamental subsets. You know that you have some sparsity. So what you would like to do is you would like to use a set of equations. If you look at these 2 equations, they are somewhat familiar to what we had before. So you have the computation of the residual has not changed for now. We're currently disregarding this part that's in gray. And you have something that's very similar to what you had before, which is phi transpose z plus the previous state, so that's your state update. But then you're allowing yourself to do some function operation here, which we'll call denoising. And the reason why you want to do something here is the following reason. Now, instead of having this simple optimization task, we also have, we know that the vector is sparse. And by that, I mean the vector on this side is sparse. So you know something about this side over here. And so it makes sense then that you're going to try to denoise. You're going to use the same set of equation, except that you're going to modify them to leverage the fact that you have some side information about the structure on the right. So this is where this eta comes to be, this denoiser comes to be. And the denoiser that's common for compressed sensing is the self-thresholding operator, which brings back your, it kind of clips your vector entries to a certain level if they're small, and if they're large, you just shrink them back to a certain amount. So this is kind of this operation over here. This is your self-thresholding operator. And this leads to the iterative self-thresholding algorithm, which is well known. And for a long time, this was an object that was studied extensively. Okay, maybe I pause for a second and see if you have some questions here. So let me know if you have any questions. Okay, so it seems that there are no questions. So let's continue. So it turns out that approximate message passing algorithm, which was first developed, I believe, for compressed sensing, builds somewhat onto the following realization. So in the first part of this tutorial, we talked about kind of the theory of graphical model. And we knew that graphical models, they can be analyzed as long as the loop, the size of the loop of the smallest loops on the graph grows large with as the graphs become big. So if your shortest cycle becomes large as the graph grows big, then you can essentially analyze the graph as if it was locally tree-like. So you can use some tree-like properties locally and disregard the fact that you have loops. It turns out for this class of algorithm that we're looking at, so iterative composite algorithms, you have something similar. And this was pointed out by Dono, Maleki, and Montanari in 2009. And the idea is that is similar, is that the fundamental object or constraint for large analysis is not necessarily the loop size, but is the effect of the cycle onto your reading. So you have to limit the effect of a node onto itself as your system grows large. And so what you have to do is control kind of the self-interference as you pass messages. When you have a fixed graph, that means that your cycles have to become large enough. But when you have a full matrix, so here we have a matrix of a certain size, what you can do is you can cancel the contribution that comes from self-interference in some sense. And this comes in the form of an unsagger term. So if you look at this, the term that we just added, if we go back and forth between iterative self-thresholding, where it's just these two equations in black, and then approximate message passing, the big difference is this unsagger term. And what this unsagger term is meant to do is it's meant to cancel the self-interference that is produced through the iterative process, or the interference that's on the order of 1 over square root of n. And when you do that, then it turns something quite fantastic happens, is that your effective observation, when you compute this, when you have both the unstaggered term and a Gaussian matrix, essentially act as a Gaussian vector as the true state plus some Gaussian vector as the system becomes large. And that is quite striking. The approximate message passing algorithm, as I mentioned earlier, was kind of put together in 2009. But the proof, one of the beautiful proof of this phenomenon is by Bayati and Montanari in 2011. I think this is worth looking at. And there they use some technique designed from or derived from statistical physics, and in particular, some of the technique created by Bolthausen to show that if you cancel if you use an unstaggered term to control the self-interference, then this effective observation that is highlighted in blue has some Gaussian-like properties. So now you can analyze the system as if it is, at every iteration, you get a new Gaussian vector. The effective observation is the true state plus some Gaussian vector. And the results of that are quite far-reaching. But this is not a tutorial on approximate message passing, so I would encourage you, if you're familiar with these results, I hope you concur with my assessment. If you're not, then I encourage you to read a little bit about this. It's very interesting. And it has gone into a theory that now is far beyond compressed sensing at this point, and it's used to prove different things. So it's very interesting. Okay, so now why is this important for us? It's important because the approximate message passing was used as a way to improve coded compressed sensing for the unsourced random access. And the first step, it's not by us, it's by these three authors, Fengler, Jung, and Kari. And they noticed that when we did the data fragmentation and the construction that I talked about, they realized that it has a structure that's very close in spirit to a sparse regression code. And then it was already known at this point that you could use approximate message passing to recover sparse regression code, and then that you could do so in a way that achieves capacity. So let's look at some of the ideas that tie coded compressed sensing to approximate message passing. So our view of coded compressed sensing when we wrote that first paper was that the compressed sensing elements would be a succession of disjoint problems. So what do I mean by that? So fragments, the original message would be encoded using an outer code, but after that you would have small fragments that are indexed individually, and then you would have a succession of manageable compressed sensing problems. So conceptually, we have the following. The first fragment would be recovered during the first time slot. So the first so many symbols of the frame. The second fragment would be in a second block, and the third fragment would be in a third block. And these CSR of a size that's manageable. So you would have L fragment, L compressed sensing problems, and then you could then use the outer code to stitch them together. So what Fengler, Jung, and Kari realized is that this is essentially, if you put things together, this is what we were doing. We were using a block diagonal matrix where each block is essentially a compressed sensing matrix. And we had a vector structure that had the following. So for one particular device, you would have a small index vector where in the first section, you have 1, 1, and everything else is 0. So that's the index of your first fragment. In the second section, you would have again 1, 1, and everything else would be 0. And that would be the index of your second fragment and so on. So that vector on the right looks like a Spark-like vector, a sparse regression code vector. And we had a block diagonal matrix. What they realized is they said, well, the complexity reduction that you're observing in your system not only comes from the fact that you have a divide and conquer approach on your vector, but it comes from the fact that you're reducing the width of the matrix quite substantially. And in fact, you're reducing the matrix so much that instead of having a block matrix, you can now use a full matrix, because your matrix, the width of your matrix is small enough to be able to use some low complexity compressed sensing type algorithm to recover the problem. So now if you look at this, if you have a single user, this is exactly a sparse regression code formulation. And you can use approximate message passing. If you had only one user, you could use approximate message passing to solve that. If you have multiple users, then you have to do a little bit of more work. And to do that, let's look at what you have to do. So this notional diagram explains the structure of an approximate message passing for coded compressed sensing. The way it works is you start here, you have at the top, I'm starting on the top left, you have the input is your received signal. This is not going to change, that's Y. Initially, that Y is equal to Z, and that becomes your residual. And then you go into your fundamental subspace, you multiply it by A transpose, so you get A transpose Y. And now you're going to, that's your act as your observation. And now you have to design the denoiser. And then after that, you delay, you update your state, and then you multiply by A, you're back in your domain, and you compute your residual. So if you go through this main loop, you get kind of the equivalent of iterative self-thresholding. And then on the right, on the left side, that's inside of that dash structure, that's the computation of your unstaggered term. That comes from the cancellation of the 1 over square root terms in your iterative message passing, approximate message passing. So that's the unstaggered term that you need. And to make it work for compressed sensing, you really need to work, the structure is the same as you would for sparse regression code, except for the denoiser. Ideally, for when you have a problem of that type, what you would like to do is you would like to use the conditional expectation as your denoiser. That would be an ideal scenario. The problem that we have is when you have k users, then the computation of the conditional expectation is very demanding. And so, so you have to come up with a lower complexity denoiser than you would otherwise for a sparse regression code. So again, let's look at this. This is an approximate message passing algorithm for unsourced random access. And let's look at the denoiser structure. So what one of the big contribution of Fengler, Jun, and Kari in their paper is to say, well, if I do the vector conditional expectation per index or per section, that's too complicated. But what I can do is I can do a entry-wise, entry by entry conditional expectation. So you're going from a vector conditional expectation to an entry conditional expectation. And of course, there's likely a performance loss in that, but this one is quite manageable. So you see that in your denoiser, if you look carefully at these equations, you will see kind of embedded in the numerator and the denominator, the fact that you have these Gaussian type distribution. So remember that for an approximate message passing problem, if you do things right, then you get this property that your effective observation is the true one embedded in Gaussian noise. So this is how you get these Gaussian-like components to your denoiser. And then what they say is that as a prior, what we are going to use is we're going to use an uninformative prior within a section. So that's the probability in some sense that one entry is non-zero. And they show that this posterior mean estimate, which is a component by component equivalent expected conditional expectation, works quite well. And T is kind of the variance of the Gaussian noise that's added to your effective observation, and it can be either computed using the state evolution, or it can be computed empirically as part of your algorithm using this approximation, and they work quite well. And if you look at this, this is a graph comparison of the original coded compressed sensing and the coded compressed sensing with approximate message passing. The two papers are here. On the x-axis, I have the number of active devices. On the y-axis, I have, again, the minimum requirement of EB over NF in dB. And then the lines that are above, I'm tracking some of the algorithms that we have seen already. The line that's below the dashed line is this fundamental benchmark that is kind of an achievable scheme if you were not bound by complexity. And now in cyan, that's the coded compressed sensing. And the one that's in red is the enhancement by using approximate message passing and show some performance improvement. So now we were outdone by this scheme, but in our back pocket, we already know that one of the lessons for low complexity is the following. And this lesson is going to come back a few times in the future schemes too, is that if you have a concatenated code, so you have an outer code and an inner code structure, if somehow you can pass information from one to the other and inform the decoding as you iterate between the inner and outer code, then you may do better. And in the current situation, the design of the algorithm for the AMP version of coded compressed sensing as an inner code that's essentially a compressed sensing problem. And the outer code was the tree code. And so what we asked ourselves is, if you can change maybe the outer code and make it in a way that's conducive to embedding it into the denoiser of approximate message passing, then maybe we can do better. And so now I return to this same diagram that we had, where this is the architecture of an approximate message passing algorithm for coded compressed sensing, except that you will notice that on the right, the denoiser now has a different structure. And what we want to try to do here is to leverage the fact that there's an outer code. So the piece that's different is that there's this outer code that's an LDPC-like bipartite graph that's going to inform our denoising. So here I want to go back and say, so far in the tutorial, we've talked about graphical based structure as a means to address complex problem, and we've also talked about concatenated coded codes as a means to address complex problem. So what we're doing here is we're mixing both data fragmentation, which we're looking at currently, and we're bringing back a tool from the first part of the tutorial, which is a graph-based technique as a means to address complex problem. So this is the structure of the original problem, where we had the tree code, adding redundancy to the different sections. And what we have is we're going to try to transform this, because we must be able to use that in the denoiser. Was there a question?
Sir, can you go one slide back?
Yes.
Sir, here the matrix A is same as the sensing matrix, which was referred as 5 earlier, right?
Yes, so that's just your sensing matrix.
It was earlier referred as 5, right?
That's correct.
Okay, thank you, sir.
Yeah, I'm sorry about the double notation. Okay, so we must transform this outer code. The outer code worked well for what it was meant to be originally, which is the stitching of the fragments together. It was very good for that. But now we want to construct one that does two things. It does the stitching that we need at the end, but also it does a dynamic denoising. So we want to be able to leverage the structure of the outer code within the inner AMP decoding. And again, the way we do that is we use two complexity reduction tricks. We're going to use an LDPC-like code for the outer code. Why we do that? Because we know that we can pass message easily on an LDPC code. We're using a graph-based technique that's good for low complexity. And this is going to be working very well for our denoiser. The other thing that we're going to use, so now if you're familiar with LDPC code, you'll notice that this is not your typical LDPC code over a binary field. This is an LDPC code that is working on a field that has a section size of, say, 2 to the 16. So it's working over a very large field. So if you're familiar with binary LDPC code, then typically you would pass a message that maybe for binary is a single value. Here we're passing messages that are on the order of the section size. So we have a belief that is over a distribution that has 2 to the 16 points. And when you do that, it can be quite demanding to do message passing over the graph. But there are some techniques. So you can do an LDPC code, you can use circulant convolution structure, or you can use an Hadamard structure to pass your message efficiently for very large alphabets. So we're using a second type of complexity reduction, which is going to be, in this case, the fast Fourier transform, but you could also use the fast Walsh Hadamard transform to pass messages on your LDPC code. And that's important because we want to do things in a very efficient manner. Another aspect that's different when you do an outer LDPC code for unsourced random access is instead of having one true point for every variable, you now have k different. So your index vector have k non-zero entries as opposed to having one non-zero entry. So there's a kind of mixing that happens when you do that over parity checks. So what do I mean by that? So if you have 2 blocks and 1 parity, and your blocks have only 1 non-zero entry. So if you have 1 non-zero entry vector coming into a check node, and you have another vector with 1 non-zero entry coming into your check node, then at the output of your check, you can have only 1 non-zero vector. But if you have a 2 sparse vector coming in on one side and a 2 sparse coming in on the other side, then you have 4 possible, the sparsity of your output is now 4. It's 2 times 2. So there's a mixing that happens. And so to avoid mixing, too much mixing, what we have to do is we have to use check nodes that have low orders. We call them triadic. We have check nodes that act over essentially pairs of fragments plus 1 parity. Maybe that's a subtle point, so I will pass on too much on that. But now the new outer code that we've designed have kind of the following structure. It pairs 2 information section to 1 parity sections, so it avoids mixing. And then what we can do then is we can force the message passing rules that typically take place onto LDPC message passing, and we can force them in some sense to work over these very large field alphabet for our problem. And when you do that, what you get is you get a very similar approximate message passing algorithm that we had before, except that the denoiser is slightly different. The denoiser remains smooth enough, so we've shown that, so you can still use the approximate message passing state evolution on this problem. And what you do is essentially you're going to tilt your priors on the graph. So you use a denoiser that uses your effective observation, and it combines it with your neighbors in the graph, which affect your priors. And if you do that, the performance improves quite drastically. So here, I have 2 graphs. On the left is a graph of performance. The x-axis is the number of active devices. The y-axis, as before, is the required EB over NOT for a 5% per user probability of error. And now I have 2 curves. The top one in blue is the original coded compressed sensing with approximate message passing in the tree outer code. And then I have the performance of the enhanced CCS AMP vector. And then the complexity is not very different for the enhanced. So you get quite a drastic improvement. So in summary, so we used quite a number of low complexity tricks to make this work over a graph. So we took the CCS and approximate message passing from Jung, Fingler, and Kyrie. And we redesigned the outer code to be able to use kind of a graph-like low complexity outer structure to get at the better denoiser. And to do that, we were able to leverage some of the graph design philosophy, as well as some of the fast Fourier transform or fast wash Hadamard transform techniques to retain low complexity and get improvements. And so it's quite interesting. I would say that from a research perspective, there is still potentially quite some slack in the design of the outer code. And so right now, we have some good performance, but there's some kind of mismatch between the model and the way we pass messages. So that's quite interesting. Any questions at this point about coded compressed sensing and approximate message passing? Okay, so if there are no questions, then I will continue. Part of the friction in using an outer code for coded compressed sensing and outer LDPC code is the fact that, as I mentioned, instead of having one symbol per section like you would if you were to decode a single user, we have K symbol per section. And that introduces some friction in your message passing. You're able to carry message passing in an efficient manner, but it's not as efficient in informing you about the likelihood of different elements in your section. So what we realized is then we could use some of the philosophy from convex demixing, where you use different sparse domains. So that's a simple twist to this. So what we're going to do at this point is we're going to create two sensing matrix, and we're going to have users randomly assign themselves to one or the other. So now we're kind of doing the equivalent of stochastic binning. Based on their messages, the users will pick either one sensing matrix or they'll pick a different sensing matrix. And the rest of the algorithm looks the same. So they will still do data fragmentation, and they will still multiply the matrix by the index vector or the aggregate index vector and transmit over the channel. But what we're able to do is we're able to run approximate message passing and decode them into as if they were two different sparse domains. So if you look at this, these are some of the curves of the performance that you can gain. Here, the graph is slightly different on the right. The x-axis is now EB over N naught, and the y-axis is the probability, the per user probability of error. The black curve is the standard coded compressed sensing with the outer code that's LDPC and approximate message passing. And now as you go into blue, the blue line says that you have essentially two sparse domain or two matrices. The dark red line is 4 bins and the dark red line is 8 bins. And here we have a Gini that tells us, like, so this is kind of an optimistic lower bound, but you have a Gini that tells you how many users are on each bin. But you can see that, like, in some sense, it's quite interesting how you go down with the performance improve as you go to different sparse domain. And you get that, I believe you get that performance because you're reducing the number of users on the outer graph per sparse domain. And so you're lowering the friction of the message passing on the LDPC outer graph. So now the CCS architecture, they keep getting more complicated, but this is kind of very similar to what we had before, except that instead of having just one structure where you're computing the residual and then you're doing the denoising, you now have one such structure per sparse domain or per matrix. So here, if I look on this notional diagram, the one that's at the forefront is the one associated with matrix A1 or sensing matrix A1. The one that's in the middle is associated with a different matrix A2, and the one that's at the back is associated with sensing matrix A3. Now you have, for this example, you have 3 sparse domain. Of course, the number of copies of the computation of the effective observation followed by denoising depends on how many sparse domain you're going to have. And one of the interesting thing about CCS AMP is that you have to compute the Onsager term that is characteristic of approximate message passing. But because of the CCS AMP problem, the Onsager term is based exclusively on the L1 and L2 norm of your state update, then they just add up in this case. So it's no more difficult to compute the Onsager term for coded demixing than it was for CCS approximate message passing. This kind of came as a surprise. And in retrospect, it makes sense, but it's kind of a super nice benefit of the simplicity of the Onsager term for our problem. Okay, so where are we with these curves? Here, we're back to the standard representation of performance for the single antenna coded unsourced random access. On the x-axis, we have the number of active devices, and on the y-axis, we have the energy requirement in terms of EB over N naught and dB. And in blue, you have the CCS AMP. That is the one that we just discussed. And then in red, you have the coded demixing with 2 sparse domains. So that's the curve in red. And then along with that, so when the coded demixing with sparse domain came to be, so it turns out that for a large number of devices, it does quite well. It performs as well as some of the best schemes that are currently existing for the single antenna scenarios. That's, say, for 200 users, it becomes very nice. But also, I wanted to include some of the other schemes that have been developed since we worked on CCS approximate message passing as a reality check. So now if you look at the bottom 2 curves, you have a polar code plus spreading curve, and you also have a curve that's based on sparse Kronecker product coding. But in general, if you look at the complexity of coded demixing, it compares it's adventuresome. No, sorry, it's advantageous compared to some of these competing schemes. Here's some of the many references that have to do with approximate message passing. And here are some of the references that have to do with data fragmentation. And I will pause for questions, because after that, we're going into the last construction of schemes for unsourced random access.
A question here?
Yes.
So with mixing, is this a principled approach in the sense that we know how much to mix before we say it's going to get worse, or there is a way to figure out how much to mix?
Yeah, so, okay, so yeah, this is a charged question. So the mixing, so if you look, when we say 3, is really the minimum size of parity that, if you have a parity on 1 block, it doesn't help much. So having a parity block that acts on 2 information block is kind of the minimum we can do for the code to make sense. So to answer your question, yeah, we pushing the mixing to as little as we can, while maintaining the property of the codes that will make sense for decoding later on. So
we're going to mix as little as possible while making
as little as practically possible for that implementation. But I will also say that that's the path that we decided to do to get some results, but I doubt that this is optimal. Like there is no optimality to this scheme. When we presented it not long ago, it was the best scheme for unsourced random access, but you can see that this has been a fast-moving field. So in a humble fashion, if you have a scheme that is currently best, then it's in your best interest to publish it right now without worrying too much about optimality, because there's a lot of smart people working on these problems. Okay, thank you for the question. So we're going into kind of a last construction, and that's an important construction because that's a construction that will generalize well for MIMO problems. We've not talked about MIMO yet, and I want to spend maybe the last half hour on these construction. So now you can think of it as the following. So we're going to use spreading-based techniques. So if you are someone who's been working or is aware of communication for a while, then maybe this brings back some memory from CDMA, where we're using spread system in some loose sense. Another way to think about spreading is based on your spreading sequence, you are now creating bins that are overlapping. So they're overlapping in the sense of correlation. So one way to view this, and I like to think about this, is the stochastic binning with shadowing. So the shadowing comes from the correlation across bin. And the fact that you have like this shadowing, the fact that you're not creating orthogonal sequences comes from, or at least is rooted partly in the unsourced nature of your system. Because users self-select the bin based on their message, it is not to our advantage to create bins that are orthogonal. As it was pointed out earlier on, if you're creating bins that are orthogonal either in frequency time or in sequences, and you're having an unsourced random access problem, then you're going to have empty bins most likely. Or it introduces a tension in the sort of the Poisson wall, although we can kind of alleviate some of these effects with multiple transmission. But you can create many bins that overlap slightly in terms of correlation. So you're using sequences, a large number of sequences that are not orthogonal, but you know that your users, because they select a random set of sequences, hopefully the realization of this selection will be such that they interfere very little on average with other users. So you're creating more bins that are correlated to be able to avoid these empty slots. So you have a better coverage in some loose sense. Okay, so having said that, here's the architecture that we're going to use to at least discuss these constructions. So we're going to take our information message, that's the top row. It has k bits, say, and we're going to partition it into two parts, a preamble, that's the first few bits, and then you're going to have a body or message payload, that's the rest of your message. And we're going to use the preamble to do two things. We're going to use the preamble to pick a spreading sequence, and so S. And then we're also going to pick the preamble to select an encoder. And then with that encoder, we're going to encode the payload. So the preamble selects the encoding and it selects the sequence. And once the encoder is selected, the payload is encoded with that encoder and creates the code word CK. And then in the traditional fashion of CDMA, what you would do is you would take the tensor product between your code word and your sequences, and that would be the signal that you're transmitting. a few points to note. So for the encoder, you could use here a polar code or an LDPC code. Polar codes are doing quite well in terms of performance of schemes by different researchers. So we can think of it as picking a polar code. And although here, when I present this on the slide, we're going to discuss it in terms of a tensor product between the code word and the spreading sequence. In actuality, you get some benefits by doing something that's a little bit more weird. So what you're doing is you're taking a tensor product between the code word and the L1 vector, and then you do a Hadamard product or entry-wise product with a very long sequence. And the reason you do that is because unlike in traditional spread spectrum system, you cannot control the interference across bins. So statistically, you're doing better if you're using the equivalent of a different spreading sequence for every code word section in some sense. But I'm going to scooch that under the rug, and for the time being, I'm just going to use the classical tensor product for the representation of our scheme. Okay, so what do you have then? You have the following. So instead of having a very long vector, I'm going to introduce a matrix type representation. So what do I mean by that? Instead of having my tensor product, which would give me a long signal, I'm going to use now an outer product between my sequence S and my code word C. So if I take the outer product of C is now, C transpose is a horizontal vector and S is a vertical vector. So when I take the outer product, I get a matrix. And if I take, so that's just a reshuffling of my entries to be able to carry a conversation easily. And if I take S Hermitian times X, then I get the 2 norm S times C transpose, the 2 norm square of S times C transpose. Okay, so in my outer product representation, I get that the observation Y that has been reshuffled into a matrix is going to be equal to the summation of a bunch of capital X, a summation of matrices, one per active user, plus some noise that has also been reshuffled to be in the right matrix form. Or I can think of it here on the right as a sum of outer product between SK prime, between the sequence and the code words per users, plus some noise. And so as an aside, if I take any SK that's and take the Hermitian times Y, then I will get this term here that's the 2 norm square of SK times the code word. And then I'm going to have some noise-like term here. And I want to do that because one of the things that I need to do with this construction is at some point in my receiver will need to decide which sequence have been selected by users. And the way they're going to do this is they're going to look at the 2 norm of this received SK Hermitian Y. So the first step in my decoding for this construction, again, is the identification of active sequences. I know that there are K active users, so what I'm going to do is I'm going to take every possible sequence. I'm going to take this sequence Hermitian times Y, and I'm going to take the 2 norm of that. And then I'm going to look at the largest element, the argument of the largest. And the reason I'm doing that is if you think of the statistics of doing that, when the sequence has been selected by a user, it has this lead component here that when I take the 2 norm of, it's going to have this very high contribution. When I pick a sequence that has not been selected by any of the users, this term in blue disappears. And so I have statistically, I have a much lower 2 norms. So that's a way to determine which sequences are active. Okay, so now let's look at the architecture of the decoding for this system. And we're going to look at it in the lens of the reshuffled Y into a matrix because it's easier to carry the computations there. So again, I have a tensor construction, but then I reshuffle the tensor into a matrix. That's just re-indexing. So I'm looking at my observation matrix Y. I use an energy detector to pick the top K elements, and these K elements are going to give me the spreading sequences of the active users. And then for every symbol, I'm going to use a LMMSC estimator to estimate the value of the different symbols attached to the different users. So this is the step that is over here that says LMMSC. And that's performed on, you can think of it as being performed on a column of matrix Y, or you can think of it as being performed on one of the symbol of the code times the spreading sequences. I'm going to do this LMMSC for every coded symbol, so over the spreading sequences. And then I'm going to feed the output of the LMMSC. I'm going to feed them to single user decoders. I'm going to take, say, the output 1 from Y1, the output 1 from Y2, the output 1 from Y3, and so on. And I'm going to use that as the observation that goes into my polar decoder. This block here is supposed to be reminiscent of a polar code. And so I'm going to do a single user polar decoding on all of these by treating the likelihood from my LMMSC. And then for the successfully decoded messages, what I'm going to do, to have a successfully decoded messages, I need two things. I need the decoding to be successful, but as is typical with polar code, I also have a cyclic redundancy check to make sure that the decoder has returned is indeed a code word. And then for the code words that were successfully decoded, what I'm going to do is I'm going to re-encode them and create an estimate of Y, and then use successive interference cancellation, where out of my original observation, I'm going to subtract the code words that were successfully decoded. And then I'm going to go around a few times along this loop. So again, in summary, I start with sequence identification, then I do linear MMSC on the symbol level. I pass the output, I sort them out and pass them to a bank of single user decoder. After that, I reconstruct my signal and I do successive interference cancellation, and then I go around into this decoding architecture. So if we want to go a little bit more in depth into what is going on with this symbol linear minimum mean square error. So now I have my Y representation. Every column corresponds in some loose sense to a symbol. So if you look at the second line here is my representation of and the outer product. So I have, if I stack the active sequences or the true sequences into my matrix S, then I can represent Y as a matrix of active sequences times a matrix where every row is a code word plus some noise. And then I'm going to make the following approximation. So remember that the first step was an energy detector that tells me or guesses which sequences are active. So now, instead of having the true matrix S of active sequences, I have an estimate of S in active sequences. So it's important that I design my system in a reasonable way so that I'm able to have a reliable SD approximation, or that most of the active sequences are in SD. But then after that, if I'm willing to live with this approximation, then it becomes a straight, or I can apply a straight linear minimum mean square filter to that. I just evaluate my covariance, and then I produce my symbol estimate for every symbol over time. Hopefully you are familiar with the linear minimum mean square estimator. And then as I said, if we dive into a little bit more into the polar code, then I'm sifting the right output of my LMMSC that goes with user one for every symbol period. So now I have one symbol coming from the first column of Y, the second column of Y, and so on. And I use these symbols that corresponds to a user to as input to my single user polar code. And then there's a CRC check. And if I'm able to decode, then I can PM. And then I want to say, when we do this technique, although I'm talking in terms of user one, we still are in an unsourced random access setting. So it's not really user one that I should say, as I should say, we're collecting the symbols that are attached with the message that uses sequence one in every slot. So it's the attachment is not to a user, the attachment is to an active sequence. So we're not violating any assumption from the unsourced random access plan. Okay, and so these techniques, they work quite well. And in some sense, some of these techniques are the best known or the best performing schemes for a single antenna. So here on this particular graph, on the x-axis, I have the number of active devices as usual, and on the y-axis, I still have the minimum energy per antenna. And then at the top, I have, for some comparison, I included sparse IDMA, which is also a graph-based technique. And then I've included these spread polar technique that's based on polar coding and irregular repetition RSA type construction, but it in spirit, it's somewhat similar. That's a polar coding with a graph that is corresponds to what we talked about in the first section. So this scheme is by Marshakov, Balitsky, Andreev, and Alexei Frolov. And for a while, this scheme in violet was the best scheme that we knew. And then there's also a construction that is a low complexity from Dmitry Churyashev and his co-author Bashir, Karmi, and Nasaji. And this scheme, this is the science scheme, does not quite perform quite as well as the spread polar that I've just discussed, but it has much lower complexity, and it is similar in spirit. It has lower complexity, and it can be used for a much larger number of users. So that's worth mentioning as well. But if you look at raw performance, then I guess this spread polar scheme that I just covered is the best for the single antenna. But one of the other benefit is that the signal structure is quite conducive to having MIMO. Okay, so I guess I had included a slides to say, okay, so we presented this scheme for the tensor because it's much easier. But what we're really doing is really, instead of having one spreading sequence that we keep for every symbol, we do a construction that's essentially equivalent to having one sequence for the first symbol, one sequence for the second symbol, and one sequence for the last symbol. And you do that because if you have a strong clash in one of these symbols, because it's a random problem, you're likely to have much less interference in the other bin. So on average, you do better. And so this is a kind of a feature that's typically not there for a spread spectrum system. And you pay for it a little bit in terms of complexity, in the sense that now you have to compute one LMMSE matrix per time slot instead of just one for all the time slot, but it works quite well as well. So that's a nuance. Okay, so now I want to switch gear and talk about the MIMO problems for the quasi-static MIMO problem. And the construction is quite similar to the last construction we've seen. So hopefully there will be some familiarity. So what do I mean by quasi-static? So here is the same problem on source random access, except that your access point has multiple antennas. And it can have quite a large number of antennas. It can have like, say, 50 or 100 antennas or fewer antennas. And we want to devise an unsourced random access scheme that works well for that. And in some sense, if you think about this, instead of being a compressed sensing problem, that is the standard problem, now you have a multiple measurement support recovery problem. So you could try a few things with this. And the fact that you have a multiple measurement problem comes from the fact that you're, instead of having one channel component, you now have many channel component. So here you have an outer product between X and the channel components. So I'm abusing notation a little bit. Now this Y is, capital Y is slightly different than the capital Y we had before. This is the capital Y that comes from, you have multiple columns because you have multiple antennas. So this is not from the tensor construction of a code word times a spreading sequence. This is from the outer product between the signal you're transmitting and the fact that it is received at multiple antennas. The channel is quasi-static, so we'll assume that it's not changing over the course of a frame. And we'll design the system to avoid collisions and to have a manageable complexity. And one of the things that has to happen when you have a large number of antennas, you need to estimate, you need to come up with good channel estimates. So one of the things that we're going to use here is we're going to use pilots, quite a large number of pilots, in fact. So the construction is very reminiscent of the polar spreading, the spread polar code that I presented, except that the preamble now is going to be divided to pick a sequence, just like before. So if you look at the top part of this is the same as the spread polar, except that now we're going to add a bunch of pilots at the beginning of our signal. So the preamble is also going to add the preamble. So the signal structure is the preamble that we're adding, and the bottom of it is the same structure that we had in the spread polar that we just reviewed. So it should be somewhat familiar. So think of it as, for now, as spread polar encoding plus some pilots. The decoding architecture is also somewhat reminiscent of what we had, except that it has an additional layer of complexity at the top. So now what we're going to do at the top is we're going to divide our received symbols into two parts. We're going to keep a capital Y that has to do with all the pilots from the different users. And then we're going to have a Y that has to do with all the payloads from all the users. We're going to use the pilot to do two things. We're going to use an energy detector, again, to here we have to resolve which pilot sequences are in use. And we're also going to use the pilot part to do channel estimation. So we have to resolve which pilots are being used, and we're going to do that using an energy detector that's in spirit, very similar to spread polar. But we also have to do channel estimation. And for channel estimation, we can think of it that once we have identified all the active pilots, then we can do a linear minimum mean square estimation for channel estimation. The bottom part of this graph looks essentially like spread polar. We come up with the observation from the multiple antennas. We're going to do symbol estimation. Now, because we have used our energy detector on the pilots, we don't need to use it on the payload symbols. We're going to come up with symbol estimates that we're going to pass in a manner similar to we had before to a bank of polar decoder. And then we're going to do signal reconstruction and successive interference cancellation, and then we're going to loop back as before. So the structure is quite similar. The pilots, the active pilots are going to be determined in a way that's very similar to the energy detector we had for spread polar, except that instead of using sequence detection, we're using pilot detection in blue over here, but very similar in spirit. And then the LMMSE is, it's a linear minimum mean square estimate in the same way that before we were estimating the active set of sequences. So here we don't quite have access to the true pilots. We have access to an estimate of the pilots. So that's why we have P hat instead of the true P. But we're acting as if we knew which pilots have been used, so we can get the channel estimation H hat. Okay, so then we have to do the symbol estimation. And here it gets, the notation clearly gets somewhat hairy. And it gets hairy because we receive for every time symbol, we receive matrices because we have several antennas. So what we have to do is we have to flatten these vectors and create like a tall vector per symbol by flattening the antennas. So what do I mean by that? This is my observation for a number of elements that correspond to one symbol, and this is for antenna M. So I have a number of antennas. So M is my antenna index. So if I understand this, and I can write my receive signal as the spreading sequence that were used times the diagonal of the code word times my channel estimate plus some noise. Here there's an approximation because I don't know the true channel, I'm using a channel estimate. But once I do that, what I can do is, this is a matrix still, so I can unravel this matrix and stack it. And on the stack version, I can use linear minimum mean square. These types of construction, they look messy in terms of notation, but if you have some background in signal processing, then you should have some sense of what we're doing. We're stacking the vector into a long vector and then doing linear minimum mean square estimation. And if you, there's a question, I believe.
Yeah. On one of the previous slides, you're doing the energy detection with pilots, right? So are the pilots also supposed to have the low correlation structure and all that?
Yeah, so the pilots are quite long, so they have like a low correlation structure. And they should be also, there's a relation between the pilot and the spreading sequences, because you're recovering the pilots. And then when I get here, I'm using like the spreading sequence matrix. So not only do they have a low correlation structure, they are very long, but they also have a relation with the spreading sequence.
Okay, thank you.
So you're correct. Okay, so but this schemes, other than these subtleties that are brought about by the number of antennas, it's quite similar to spread polar. And now I want to show the performance of this scheme, and I want to talk about the competing schemes. So the first competing scheme, this scheme is a tensor-based modulation scheme. And we have to give credit to the authors because I believe they were the first to look at on-source random access for multiple antenna, large number of multiple antennas. In their scheme, they do not use pilots. Rather, what they do is they create a code book that's based on a tensor structure. So I'm going to create the code book based on a structure that looks like this. So I'm going to embed a tensor structure in my code. And then this, when I send this signal, it's still going to be tensored by, the channel. So the receive signal looks like a tensor structure. That's my original code word, the tensored with the channel itself. And I have one such rank 1 tensor per user. So that is a summation over K. And then Z is noise here. And what they decided to use is they decided to decode this with a canonical polyadic decomposition, CPD. And one way to understand this algorithm, so they used this algorithm family that existed already. And one way to understand it is, or at least for me, one way to understand it is this is a bit of the equivalent of singular value decomposition, but for a tensor that has a much greater number of components. And then there exists some iterative ways to do this because you have to manage complexity in some sense. And so what you're doing is, in some loose sense, you're doing a nonlinear least square for every section of your tensor, flattening out the rest. Then you go from section to section. These algorithms, although we'll see that the performance of this particular algorithm for unsourced random access is not state of the art for multiple antenna, but this class of algorithm has found a lot of application in machine learning, say for instance. So it is a very good class of algorithms to know for in a broader context. And then I also want to introduce a structure. So spend a minute to introduce a structure that was introduced by Amadi and Duman. And this is a very low complexity structure. Here again, they use a large number of pilots. So it's much closer in spirit to what we're doing. And they also use a single user polar encoding. But they're very careful of complexity in their scheme. And so what they do is, instead of having one preamble, they divide their preamble into small snippets. So the WP1 is the information bit in preamble 1, and then the second one should be WP2, and then WPJ. So you have J section of preamble. And then these are employed to select rows into a Hadamard matrix. So B is a Hadamard matrix. And you use the pilot bits to select a row. And the row is what you transmit for this component. And then you do the same for the next snippet of preamble. You select a row out of a Hadamard matrix and you transmit this second one, and you continue like that. And one of the properties of the Hadamard matrix is that it's very easy to recover because you can use the fast Hadamard transform to estimate which rows were selected. And then based on that, essentially, you recover the pilots. And then once you have the pilots, you have also a channel estimate. You can pass that through a polar encoder and decode in a manner that's very efficient. And if you do that, then you get good performance with very low complexity. So I am a big fan of this. Okay, so let me present these results. Same graph that we've seen before. So on the x-axis, you have the number of active devices. But now we have many more antennas. So you can see that the system can support many more devices than before. And also, we've reduced the number of channels used by a factor of 10 because we now have like 50 or 100 antennas. On the y-axis, you have the same required energy EB over a naught. So the nature of the graph has not changed. And now you have the performance of the different system. The blue curve is the tensor-based method that does not use pilots. So you can see that, and this is also a computationally a complex method. And then this second curve is based on having a large number of pilots, but instead of, it has a lower complexity than our scheme because it uses a match filter instead of using this bank of linear MMSE that have a local matrix inverse. So you get good performance with low complexity. And I should mention that this is a scheme by Fengler, Musa, Jung, and Kyrie. This violet scheme is the orthogonal plus pilot. This is the one that has a bank of pilot that are based on Hadamard and then the single user polar decoders. This is this performance. And then the Fissura scheme is our scheme that uses essentially, it's in the spirit of spreading and polar or spread polar. And it performs quite well, but the level of complexity is a couple of order of magnitude more than the violet scheme. So we're buying a little bit of performance at the cost of a lot of complexity. And the scheme that I talk about is really this pinkish curve that says pilot and LMMSC. And the Fissura scheme does a few more tweaks of the following nature. So you can use
To interrupt, I think just to remind about time, we have to close.
I think so I will wrap up with this.
Thank you.
Yeah, so you're doing tricks like re-estimation of your symbol with the bits that you're most confident about from your polar decoder and things like that. So you're buying a little bit of performance at the price of complexity. But I think they're a very good scheme. Do I think that these are the best? No, I don't know. I think it's hard to say, but currently, in terms of performance, is the best. Okay, so I will skip these sections, and I want to come here. Okay, so talk about. So I want to conclude the formal tutorial because I believe I'm out of time. Actually, she was quite kind to remind me about time, but I think this is we're done. We're out of time. Is that right?
Yes, we are. I mean,
okay.
Yeah.
So I will conclude with this slide. It talks about future. Okay, so if you are interested in doing research in on-source random access, there are quite some interesting problems that are still pretty open. One of them is we've collectively, the community has several schemes for one antenna, and it has several schemes for multiple antennas on the order of 50 or 100 or like large number of antennas. And when you have a large number of antennas, what happens is the users are statistically separated in the signal space, so you don't need to worry about interference that much. But there's not too many schemes for a few antennas. So that's kind of like a pretty wide open area. And then the channel estimation, so we assume some very nice quasi-static models. So it turns out that for multiple antennas, there's the two extreme again. So if the channel is essentially static or quasi-static, we have some good scheme collectively as a community. And if the channel changes with every symbol, there's some, you can take advantage of statistical properties, and we have some good schemes. But if the channel changes significantly but slowly, there's not too many schemes. And here, maybe I should say that there's an opportunity to use some of the new philosophy of unrolling URA iterative algorithm and using type of machine learning. So for instance, there's this philosophy is outlined by Sabalal and Sri Krishna Bhashyam. They use kind of the deep unfolding of some algorithm, and you could use a similar spirit here. So that's a wide open research problem area. There's just maybe one or two pieces of work on heterogeneous classes for URA. There's a philosophy that for small and fading channel, maybe incremental redundancy and URA could be used. So there's a quest for universality. That's a good opportunity to do some research. There has been significant work and papers on over-the-air federated learning. For a single antenna, some nice properties happen for a single antenna, and it's related to on-source random access in some close sense, but it's not clear what happens when you have multiple antenna, what to do there. So over-the-air federated learning for multiple antennas seems to be interesting, at least for our group, that's an interest. Cell-free URA instead of having a single cell would be interesting. And then you also have some connection between on-source random access or some of the scheme we're doing and things in theoretical computer science like sketching. And they're more worried about the order of things, but and they have some very nice constructions. The community that works on on-source random access and has been driven by algorithms that are implementable and testable. And so it's a bit of a different flavor, but there's definitely some connections there that could be explored. And Okay, so I want to say that if you are interested in this, you can snatch the slides from their website, but also I would like to say that if you want to reproduce some of the results, we put our code on GitHub. So you can at least reproduce some of the results. If there is code that you're interested in that's not on GitHub, there's typically a propagation delay between the code we use to publish and the code we push on GitHub, but we respond well to that. I have also made the LaTeX source available for the slide. So if you want to look at the plot and see how much better your scheme is compared to the state of the art, you can use these plots. And I would like to thank you for attending this tutorial. And on that, I will conclude. I can answer a question for a little longer, depending on how long you want to stay. But thank you again for this opportunity.
I would like to